So I think it's great to have, I thought it was a good idea to have a discussion about the two complementary methods of studying water mass pathways in the ocean, and those are the Lagrangian methods and Eulerian methods. So we invited two people that would present us with studies that use both of these methods, so that kind of we can do some compare and contrast, and maybe have a brief discussion on the benefits of each of them afterwards. So for the Lagrangian methods, we invited Stephen Kelly from the National Oceanographic Center in Southampton. And as he said, congratulations on your PhD. This is very exciting. And we're very happy to have you here. And we realize it's a little bit late on your side, so we're taking away from your evening here. So
I'm not a morning person at all. I prefer this anyway. It's fine.
Okay. Okay. Well, great. So if you can share your screen then, and we're very excited to listen to your presentation.
Oh, thank you very much. Slideshow. There we go. So as mentioned before, I'm going to be giving the talk about Lagrangian modeling of connectivity in the Arctic Ocean. And then on the right of the screen, I've just got a list of the institutions that have funded the research that I do. So the structure of the talk that I'm going to give, it's going to be about a 50-50 split. First half, just talking about Lagrangian modeling in a general sense. And then after that, I'm going to give a brief example of a paper that is currently in press in Earth's Future as an example of some of the cool stuff that you can do with Lagrangian modeling in the Arctic Ocean. So when studying marine connectivity, the first thing really you have to do is define what we actually mean by marine connectivity. I've copied in a definition from Condi et al. 2005 there, but the short answer of it is describing how spatially separated parts of the ocean are linked to each other in space and time. So what timescales does it take for currents to connect one region to the other? What pathways do they take? And depending on what problem you're looking at, you can pull out various different metrics that can answer various different questions. And Lagrangian modeling is a powerful tool for that. So as we've already briefly discussed, the two main approaches you can take are either Eulerian, which we're going to have a talk about later on, so I won't say too much about now, or a Lagrangian approach. And the main advantage of taking a Lagrangian approach is that compared to Eulerian, it can be computationally a lot cheaper. So it makes use of pre-existing model output, which is the most powerful part of it, because you're adding value to something which has already been done. And by using these pre-calculated model means, you can use incredibly high resolution models that might be prohibitively expensive to use from a purely Eulerian approach. It takes less time if you're not having to do a long online run of the model, but there are downsides as well in that with this Lagrangian approach, convective processes, diffusive processes aren't explicitly solved for. So depending on what package you're using, you can manually add an attempt at diffusion, but it won't do that as rigorously, or in the case of convection at all, as Eulerian will. In the examples I've used Lagrangian modeling for, I've made use of the NEMO model. So specifically the high resolution 12th degree Orca 0083 N06 configuration run. And I can talk in more detail about what the forcings used to run this model were later, if anyone is specifically interested. The key point to take home from it basically is we're using 5-day mean model output, and in the Arctic Ocean, 12th degree resolution roughly corresponds to 3 to 5 kilometers horizontal resolution. So that's eddy permitting, but due to the small Rossby radius, not fully eddy resolving on the shelves, even at the highest resolution available to us. So how exactly does Lagrangian particle tracking work for anyone who isn't familiar with it? I've just taken a simple cartoon of a model grid cell. The NEMO model that we're using uses the Arakawa C grid, where you've got velocities saved at each face of the grid cell. And the particle tracking package, I use Ariane, but TrackMass or Parcels or various other software packages are available. It works by calculating the timescale required to get from wherever your virtual particle is in the model grid cell to each of the grid cell faces. And then the shortest timescale corresponds to the one that adds to the trajectory. You then repeat this for the next grid cell, and so on. You can build up a long model trajectory. And the beauty of this is that adding extra particles isn't the dominant factor in determining the cost of the experiments. So you can add thousands of them and get generally a good picture of what is going on in this case, the Arctic, but wherever you want to look. The trajectories you get out from this is, as Eric Van Sabeel called, and I quite like the term, spaghetti, if anyone was at Ocean Sciences this year. You can gradually build up pictures of what's going on like that. This is from a different experiment I've looked at, and just scroll through, gradually building up. I'm coloring it based on how long these trajectories have been running for. You can build up a picture of where your discrete trajectories are going, and depending on the problem that you're trying to address, you can either consider the spread of them. If, for example, this was work looking at oil spills, you can look at the timescales to get to different places, and you can very clearly see it's picking out different major pathways. So, powerful tool for understanding connectivity. And the specific case study that I want to talk about where we've used this is a slightly dramatically titled paper looking at changing transantarctic connectivity between the North Pacific and the North Atlantic Oceans. So it's a problem which lends itself very well to studying marine connectivity, because you're looking at how something has got across from Pacific to North Atlantic, takes multiple years to get there. So, and you're looking at how this has changed over various years. You need to run lots and lots of new experiments, and doing that from an Eulerian approach would be, you have to have a lot more computational resource than they let PhD students have. So the motivation for this specific study is trying to see whether or not anything interesting has happened that could be linked to the connectivity between the two basins increasing. So in the late 90s, a diatom, which the past hundreds of thousands of years had always been only in the North Pacific, was recorded by a continuous plankton recorder in the North Atlantic Ocean, which is not where it naturally should be. And the idea is that, okay, how's this come across via changing Arctic currents? And not only is this important specifically for one species of diatom, which someone may or may not care about, but as kind of a, completely lost the word I'm looking for, an example of increasing connectivity in a more general sense. So to investigate this, we released 1,000 particles in the Bering Strait every month between 1970 and 2003, track their progress for 10 years and see where they go, basically. How long does it take them to reach about the area that this diatom was recorded? How does that vary seasonally? How does it vary by year? And importantly, is it changing by the pathway it's taken? Other important questions that there might be contributing to the change in connectivity, changing environmental conditions along the route, which in principle you can pull out with a Lagrangian approach. We haven't done it here. This is something that we're hoping to work on in future. This is just the first step of hopefully a bigger project. But the idea with this, how has the circulation changed, and is there a way we can objectively quantify this using a Lagrangian approach? So we use a set of what we call traps. You can see these blue regions in the figure on the left. And the idea being, if any trajectory spends a time step in any of these traps, that's logged and added to the trajectory history, and we can separate based on which traps a particle has or hasn't been through, what pathway it took to get to the Atlantic Ocean, and we've color coded them, as you can see in this kind of cartoony schematic on the right. And just an example that what we're doing with this classification is basically doing what you'd expect to do. You can see you've got the transpolar drift shows up in all but the green route as the dominant pathway transporting things from the Pacific side to the Atlantic side. You've got something a bit different going on with this middle on the left, and C, the green pathway, and then F in the bottom right is things that weren't categorized. But they're only about 0.3% that didn't fit in, so we ignore them. They don't do anything interesting. How many trajectories take each route? This is where you start to see that the green route might be something interesting, in that you've got these spikes in the pathway that hugged the North American coast before filing through the archipelago. Most of the time it's not there or negligible, but occasionally it happens. We've also got some variability going on with the other routes, which I can talk about later if people care, but it's not the main focus of this story. The important take home from this, the green route is either open or closed. And why should we care when it's open? It's only, you can see from this graph, even in the top case, about 0.1 to 0.2, so 10% to 20% of trajectories taking that route. The reason we care is that it's an abnormally rapid route, and it can take as little as 2.5 years to get from Pacific to 60 North in the Atlantic Ocean, compared to a more usual timetable of 4 years for that route. And in the context of ecological connectivity, if you're thinking about diatoms, something that's alive, then minimizing the time that you're spending in harsh polar conditions for subpolar species is potentially important for making it potentially a more survivable route. So obviously more research needed to see if conditions are changing to allow for it to survive, but this in itself is potentially something interesting. We then get on to trying to understand the reasons why this change might be happening. We've got two metrics which both describe the cyclonicity in the Arctic. You've got the Arctic Oscillation, which I'm sure everyone knows about, and the Arctic Ocean Oscillation, which is something that Andrei Proshtinsky has come up with. It's based on a two-layer idealized model that describes the ocean's response to the atmospheric forcing, whether it's more cyclonic or more anticyclonic. In short, in this figure, we can see cyclonicity is when the blue line is positive, and anticyclonicity when it's negative, and mirror image for the orange. When the orange is negative, that's abnormally cyclonic. And I've plotted the green stripes are the releases where we see these spikes in particles following the anomalously short timescale route, and they correspond to an anomalously cyclonic Arctic, especially in 1989. It only really shows up in the AO, not in the AOO or 75. But the reason we think this is particularly important is that anomalously cyclonic Arctic drives Ekman convergence in around the Beaufort-Jaya region. By continuity, induces slope and sea surface gradients and drives barotropic current towards the Canadian archipelago, where in more anticyclonic conditions, this pathway would be blocked, or at least mostly blocked. And the idea being, this is our explanation for why we think this enormously short trajectory may exist. And if this shorter pathway exists, coupled with a changing, warming Arctic Ocean, potentially could lead to an increase in ecological connectivity between the two basins. So jumping to the conclusions for the talk, using this particle tracking technique, which is computationally efficient and allows us to run many of these experiments, we were able to identify an enormously short timescale connecting the Pacific and Atlantic Ocean. We've been able to identify the reason we think this is going on, specifically anomalously cyclonic Arctic, And then we see this as the first step of more research, trying to work out exactly what's going on in changing connectivity. You need to be able to start looking at temperature, light regime, ice cover, to properly understand whether any major shift is occurring for connectivity between the two basins on an ecological context. So that's about all that I had to say for this. I've got a few funders that I need to acknowledge for all of this research, but if anyone has any questions, I think now would be a good time to open it up, and hopefully this has been about 15 minutes. Sorry if I've overrun or underrun. I've not been timing.
I have a question.
Yep.
Hey, Stephen, it's Mike.
Hey, yeah.
So I have a few questions, but I will try to limit myself. It's great and really interesting stuff. I mean, the figures are very intriguing and kind of a new way of looking at things. So I love it. But I have some questions. So I mean, first of all, are you proposing that there's some kind of a trend in circulation regimes?
So we can't say for sure whether there's. So we can't say for sure whether there's a major trend. You can see with this blue route seems to be increasing, pink route seems to be decreasing, but equally we start at 1970, which is relatively close to the start of the model spin-up period, which was in the 1950s. So I've not looked enough to stick my neck out and say that there's a trend as such. What we are seeing is a very binary on-off kind of regime where, specifically with this green route, the one that hugs the American coastline and avoids the transpolar drift, this is either open or closed to a significant number of particles. And what we're suggesting is that atmospheric forcing, specifically large-scale cyclonicity in the Arctic, is what's responsible for either opening or closing this route.
Okay, cool. I had more questions, but I'll let someone else jump in.
Hi, this is. Oh, go ahead, Phil.
Okay, well, it was just to ask a sort of a technical question also. Do the particles undergo three-dimensional advection, or are you moving them along isotropes or isopycnal surfaces, or how does that work?
Yeah, so they can move fully three-dimensionally based on the advective component velocity saved as the model means. So there's no mixing or anything going on, but other than that, they can move fully three-dimensionally.
Thanks.
Hi, this is Hailong. I have a fairly technical, interesting study. Technical ones. You identified 1,000 particles. I would imagine that that relies on how big of an area you release the particles and how long you run the simulations, right?
So they're released in a strip across the Bering Strait, and they're tracked for 10 years. But an interesting thing that popped up in the reviews for the paper, and so the final version, we've now added this in, specifically being the 1,000 particles. Obviously, the results are only as reliable as the experiment itself, and adding more particles to your experiment will make it more reliable. We've done some subsampling to check that this setup is viable. You can randomly subsample and take an order of magnitude, and it still doesn't affect the absolute shortest trajectories too much. So we think we're doing something right.
Thank you. By the way, I'm not the reviewer.
No, that's no trouble at all. No, this specific comment came from Eric Van Tadeel, so I know who that was.
I didn't know if we were supposed to be raising our hand or not, but thanks, Stephen. That was a nice presentation. I had, again, another technical question here. So the model you're taking this from is from NEMO. And assuming you have to use the output from it, you need three-dimensional velocity fields. What's the temporal resolution, ideally, that you're outputting this? Maybe you said it somewhere, but I mean, daily? Is it monthly? Is it yearly? And do you think that that temporal resolution would affect your results much?
So we're outputting particle positions daily, and the velocity fields that we're using as the input to drive Lagrangian experiments are saved as 5-day means. So obviously higher resolution would always be better, but especially with 12th degree, it's a hell of a lot of data to save, and 5-day means are the only thing that we have for the full day. We can't get any better than that, basically.
Right.
So, yes, yes, more would obviously always be better, but 5-day means, when you're looking at connectivity timescales of 2, 3, 4 years plus, it's pretty good, I'd say.
So I was thinking too, in terms of lower resolution models, like could you get away with monthly mean data? Would that not be good enough for this sort of algorithm?
In principle, you could do it. Whether it would be particularly meaningful or not,
Okay.
I'm not going to stick my neck out too much, because everything that I've done has been with the 12th degree resolution run at 5-day mean frequency. So this is me speculating rather than anything else. But part of the reason that we use the 12th degree run is that it's at the very least eddy permitting. And if you start looking at longer time scales and coarser resolutions, then you're not going to be resolving eddies at all. And if you're not doing that properly, then that's an important mechanism for transport that's been lost. And so the results will become less reliable, but whether you'd be able to get something useful using monthly means, perhaps, I don't know.
Okay, thanks.
Can I just follow that up again? This is Mike again. I mean, so when you do this kind of work, Stephen, I mean, how do we know that you've maybe asymptoted towards, the right resolution in time and space? I mean, you could do it with your 5-day means. You could do it with 50-day means. You could do it with 500-day means. I mean, you could redo it with lower resolution and show that you're asymptoting to something, or maybe you're not. Maybe if you did 5-day means, you get one result. If you do 2-day means, you get a totally different result. I mean, how do we know this?
The short answer is we can't check, just because we've used the highest resolution that is possibly available to us. We could do lower resolution experiments. That is a good idea, actually, to try and work out how much these results are sensitive to what resolution we're using. Yeah. But the thing I would caution against on that is one of the important things we're finding here is passage through the Canadian archipelago. So in time, obviously, cutting the resolution won't affect that. If you cut the resolution in space, then things will fundamentally change, because you're trying to resolve a very complex geographical region. Whether or not using monthly means or even longer scale means would affect it, again, unfortunately, pass is the answer. I'd like to be able to say something more useful, but I'm not really able to speculate too much.
So this is Wisław. Can I have one more question?
Yeah, of course.
I was a little surprised by the very spiky behavior of the green solution in your diagram. My understanding is that the cyclonic circulation during the time of late 80s and the 90s has lasted for at least several years, according to that plot that you, no, not that plot, the one that you showed the diagram, time series of solutions, the various lines, time series.
Where are we?
That one, yeah.
This one?
Here. Yep. So if I look at the green solution, it looks like it's just a yearly spikes at most. And my understanding again is that the late 80s, early 1990s, cyclonic circulation was persisting for several years. Is this some methodology issue here, or this is something else?
So the main peak that we see is the 1989 peak, where it's unprecedented cyclonicity. It does remain cyclonic for a while afterwards, but the main peak we're seeing is at the main peak of this as well. And it's also important to remember that the trajectories, while it's a spike at a single year, it's the trajectory spending at the very least 2.5, typically about 4 years worth of forcing. So it has to be consistently cyclonic at the right time in order to allow for this to happen. That's not a very good answer for 1975. We need to understand a bit more what's going on for that. But the short answer is that for the main peak, it coincides with a sustained period of cyclonicity. Why it's as short and sharp a peak as we're seeing, again, don't entirely know the answer, but the fact that it's the start of the period and then it remains cyclonic from about this 1989 and then 4 years of very, very cyclonic relative to what the Arctic normally is, forcing.
Thank you.
The idea being that's about the only time it's sustained throughout the route, which is why we're seeing this peak.
Okay.
Thanks, everyone. I think we're going to try and move on to the next talk, so we have enough time because we only have about 20 minutes left.
Oh, apologies if I took too much. Sorry.
You're fine.
All right, our next speaker is Yashu Zhang. She introduced herself earlier. She's now at PMEL in Seattle, and very pleased to have her present the work that she did on the Beaufort Gyre using Eulerian methods.
Thank you, Robert, and thank you, everyone. Well, this is essentially the same presentation I gave a month ago in the Ocean Sciences meeting, so apologize to those who already heard it. So this is about the Labrador Sea freshening linked to Beaufort Gyre freshwater release. This is a collaboration between me and Robert Wire, Tyrone Verma at Los Alamos, Mike Steele in University of Washington, and Wei Ching in UW and Onoa PMEL. So our paper is currently in review by Nature Communications. So the Beaufort Gyre region is the largest oceanic freshwater reservoir in the Northern Hemisphere. So in this figure, the color shows the Arctic freshwater content. You can see that the high value over the Beaufort Gyre region, which is enclosed by this green dashed box. And the reason why high volume of water can be accumulated here is because of the Beaufort Gyre, which has very strong decadal variability. So during some years, when the gyre is strong, it can accumulate water in the middle of it, while in other years, when the gyre gets weak, the water will be released downstream into the Atlantic. So thanks to the Beaufort Gyre exploration project, we start to get a continuous observation over there. And what we see is there is a continuous increasing trend starting from 2003. And by 2017, the value is already 40% above its long-term climatology. So it is thought because of the persistent anticyclonic wind plus the sea ice decline at the same time. So you can imagine that if in the future the water starts to, the high accumulation starts to collapse and the water is getting released, it will have very high impact over the Atlantic on the meridional overturn escalation. So it will be similar as the previous Grisling anomalies, especially during the 1970s. However, the impact of the Beaufort Gyre freshwater on the North Atlantic is largely unknown. So there's three specific questions. First, we don't know its release pathways, whether it's through the Canadian archipelago or through the Fram Strait. It's unknown. Second, we don't know its most affected areas. So which of the deep water formation site is most affected? And finally, we don't know how much surface salinity change it can bring. So in this research, we use the recently developed global eddy-permitting ocean CS model. We call it a E3SM version 0, configured for high altitude at 0.3 degree. So we use this model to investigate this problem. So it has the POP2 as the ocean component and size 5 as the sea ice component. So this figure, I compare the Arctic bathymetry for the 1 degree model and the 0.3 degree model. So in our version of the model, we bring down the horizontal resolution over the Arctic from 40 kilometers to 14, and then also increased the vertical levels from 60 to 100. And we turn off the GM eddy parameterization. So using, oh, by the way, so you can see that the Canadian archipelago is much better resolved. So previously it was like a big chunk of island, and now we see all the small islands here. So we forced the model using the use the core 2 atmospheric forcing from 1948 to 2009. We forced the model for 3 cycles, making it 186 model years in total. And we used the last cycle for analysis and tracer diagnosis. So first, we want to see whether our model is able to get a good freshwater content. So the map on the left shows the area of interest, and the Beaufort Gyre is enclosed by this black box. So what we do is we calculate the annual mean freshwater content over this area and plot it on the right. So both the blue curve and the orange curve are the model output. The only difference is that the blue is for annual mean and the all-month mean, and orange is for summertime only. So, and also we overlap the observation in the green curve, which is what I showed before. So you can see that we have the freshwater content have a very strong decadal variability, and most importantly, it can reproduce the rapid increase as seen in the observation. And actually, this increase can be traced back to 1996. And if our model is correct, you can see that currently the freshwater anomaly is already double its historical maximum, which is found in 1983. So from now, we're going to focus on 2 periods. So the first one is the fast release, which is 1983 to 1995. And the second period is from 1996 to 2008. So we implemented 2 types of tracers into the model. The first one is a dye tracer, which we use it to track the volume transport. So it's initialized as 1 in the Beaufort Gyre region from the surface to the depth of the reference salinity. So it's like a 3-dimensional, like a volume of water, and it's 0 outside. When we do the integration, we reset the volume, the value inside this Beaufort Gyre region to 1 at each time step, and outside it's advected and diffused just like a passive tracer. The second tracer, which is quite unique in our research, is we call it a salt tracer. So it tracks the freshwater transport. It's essentially the same as the dye tracer, but when we initialize as its local salinity value, and when we reset, it's also get reset to the local salinity. So this is an animation showing the tracer distribution at the ocean surface in the fast release case. So the left is for dye tracer, and the right is for the salt tracer. So I want to point it that, as Stephen just introduced, so this tracer is, these 2 tracers are Eulerian scalar tracers. So they're not the Lagrangian tracer particles as Stephen just introduced. And they are for diagnosis only, which means that there's no feedback to the ocean dynamics. So now let's take a look at the results. So first, we want to know the fate of the Beaufort Gyre freshwater in different scenarios. What I show on the left are the vertically integrated dye tracer concentration by the end of each 13-year simulation. So what we see is that on the left, the fast release case, The tracer tends to be transported towards the Canadian archipelago into the Baffin Bay, and then Labrador Sea, and finally into the subtropical gyre. But in the fast accumulation case, the tracer tends to be locally accumulated and then transport into the west. So on the right, it shows the difference, which is fast release minus fast accumulation. So you can see very clear what I just said. So the next step, we want to look at the Beaufort gyre-sourced freshwater transport at major ocean gateways. So we focus on 4 locations: the Lancaster Sound, which is here, the Narrow Strait, which is here. So both of them are the 2 major Canadian archipelago pathways, and then Davis Strait, and then Fram Strait. So in all the ocean models, in any of the ocean models, so we can use this first equation to calculate the freshwater transport. So here the S is salinity at each gray box, and then SREF is the reference salinity, and V is velocity. But with the help of the 2 passive tracers, we can diagnose the freshwater transport only sourced from Beaufort gyre. So here the alpha BG is the dye tracer, and the DBG here is the salt tracer, which is essentially alpha BG times the salinity of the Beaufort gyre. So we calculate this freshwater transport only from BG at each location, and then plot it with time. So different colors show different locations, and the solid line is for the fast release case, and dashed is for the fast accumulation case. So we see that, so basically in the Lancaster Sound, you see a very clear high value, say, in the fast release compared with the fast accumulation. So it's the same thing for the Narrow Strait. For the Davis Strait, it collects water from both of the locations. So you can see that by the end of the simulation, the fast release have the value almost like 2 times higher than the fast accumulation case. Fram Strait, the value is much lower, and second, the fast release case does have like a higher value as the during this period, but in the later period it starts to decrease. So we conclude that the Canadian archipelago and the downstream Davis Strait is the main route for Beaufort gyre freshwater to enter the North Atlantic. So in the next step, we focus on the last 5 years. So what we did is we do an average of the last 5 years and put it into a bar plot. So the box here show the, so the bar shows the total liquid freshwater transport, and the box is the climatology. The dark value is for the fast release case, and the light color is for the fast accumulation case. So we see that for the Narrow Strait, we do have a higher value for the dark color and lower value for the light color. But another important part is we further put the Beaufort gyre component into the dash. So we see the increase is mostly caused by the Beaufort gyre component. It is the same thing for the Lancaster Sound and the same thing for the Davis Strait. But the Fram Strait is a different story. So first, the Beaufort gyre is not a dominant component anymore. And second, the increase of the dark color bar is not only because of the BG, but also because of the non-BG component. So we conclude that the Beaufort gyre freshwater is a dominant factor for the freshwater transport at Davis Strait, but not for Fram Strait. Finally, we evaluate the impact on the downstream salinity. So at any downstream grid point, we can write the salinity into 2 components. First is the Beaufort gyre component, and the second is the non-Beaufort gyre component. And further, we define the difference between the local salinity and the non-Beaufort-Gyre salinity as delta SBG. So we call it the impact of Beaufort-Gyre freshwater on the downstream salinity. So let's, for example, if we have no freshwater, no freshwater from BG, so which means the alpha BG is 0, you will have S equals S and BG, which means the difference between the two will be 0. The delta is 0 means there is no BG impact. As you increase the alpha BG value, you're introducing more and more fresh water into the system. So you are getting the S lower and lower, and this difference will be more and more negative. So it means that the more the negative the delta value is, you will have a greater impact from the Beaufort-Gyre. So we calculate this delta value at each of the locations, and we plot them on a map. So on the left, the two plots show the upper 200-meter delta values averaged over the last 3 years of each of the simulations. So what we see is that, so if you look at the color bar, so the negative value is on the left, which is the dark colors. So you see that the Beaufort-Gyre have very obvious impact over the western side of the Baffin Bay, and this impact continues over to the Labrador Sea, to the western Labrador Sea. If you look at the second plot, which is the fast accumulation case, the pattern is very similar, but the value is almost half the size of the left one. And if you look at the figure C, which is on the right, so this is the difference between the two maps, and you can see that very clear large impact for the first map, and actually the salinity difference over the Labrador current can be as high as 0.4 PSU. And if you calculate the value over the blue box, the western Labrador Sea, it's about 0.2 PSU. So this is the summary and discussion. So in this research, we are using a global eddy-permitting ocean CS model with tracer diagnosis to answer 3 questions. The first is, what are the Beaufort-Gyre release pathways? So we find it's mostly through the Canadian archipelago and the downstream Davis Strait, rather than through Fram Strait. And second question is, what's the most impacted deep water formation site? So we find it's over the western Labrador Sea. And finally, how much of the salinity change can it bring? So we find a 25 millisiever drop of Beaufort-Gyre freshwater anomaly, which is measured at Davis Strait, can bring a 0.2 PSU drop in the western Labrador Sea and 0.4 locally along the Labrador current. So we want to put our values into a bigger, into a context and see how large or how small it is compared with the Greenland meltwater. So we found 3 excellent research papers, and all of them are using a high-resolution model for the Greenland meltwater. And these are the numbers they find. So I won't repeat all the numbers, but you can see that our number is almost the same order of magnitude as the Greenland meltwater, maybe even slightly higher. So we see that given that the present Beaufort-Gyre freshwater content anomaly is already twice the case we studied here, so we anticipate the impact of a future rapid release of Beaufort-Gyre freshwater on Labrador Sea salinity could easily exceed those from the Greenland meltwater fluxes. And finally, I want to say that now all the comparison is really qualitative. So it will be really interesting to examine the individual impact and interactions among the Beaufort-Gyre freshwater, the Greenland meltwater, and the Arctic sea ice export, mostly from the from Fram Strait. So it will be nice to compare, to quantitatively compare three of them, see how much they impact the subpolar North Atlantic. So if anyone is interested in this, we will be happy to collaborate and work together. So I'm done and ready to take questions.
Great, thanks, Yasu. We have a couple of, we have 1 minute for questions, and hopefully some people can stick around a little bit longer if there are more questions. So we have a little bit more time for discussion. So let's go ahead.
I have a question. It's Tom Hain.
Mm-hmm.
So I'm curious about your salinity change numbers, the 0.2 and the 0.4. Mm-hmm. And I have a couple of questions that relate to that. The first is your southern boundary condition. Do you allow the anomalous fresh water to reduce leak out into the subtropical Atlantic, or is there a solid boundary and it has to recirculate?
So yes, so far we allow it to be recirculated back into the Arctic. Okay. So we didn't put any restriction on that. Yeah.
Yes, thank you. And then the second question is to do with the importance of sea ice affecting subpolar North Atlantic salinity. So if I understood correctly, you've not accounted for any changes in sea ice export from the Arctic. And there's some evidence that when, for example, the Beaufort Gy is spinning up, which would be your fast accumulate case, that the transpolar drift accelerates and the ice flux through Fram Strait also accelerates. And so there can be a compensatory impact on subpolar North Atlantic salinity. So can you comment on that or maybe estimate the size of that effect?
So yes, you're right. So we didn't consider any of the sea ice component, but I have to say this is a really good point. And it will be really interesting to compare, as I said, to compare the liquid freshwater part and the sea ice export part. So like, do they like have a positive correlation or a negative correlation? And we already find that, so like from here for the liquid freshwater part, the Davis Strait definitely have a much more export compared with the Fram. But Fram, the sea ice export is much more there. It's a liquid part. So it will be really nice to compare the total freshwater transport at the two locations.
Thank you.
Are there any more questions?
Well, Wilbert, you proposed at the start of this that we have a discussion about the relative merits and strengths and weaknesses and approaches of these two different Eulerian versus Lagrangian. I'd love to do that. I don't know if we have time now or how we do that, but.
So, and Christine, she suggested maybe to go over for another 10 minutes or so that we can have this kind of discussion still. And also maybe a couple of minutes for a community update. So if you want to go ahead and start that discussion, that would be much appreciated. And people that have other commitments, they probably have to sign off anyway. So
I don't want to start the conversation. I thought maybe Joshua and Stephen could give us their thoughts.
So one way maybe to ask is to what extent would Yashu's study have been possible using Lagrangian methods? How different would it have been? And on the other end, how different would have been the Stephen's study if he had to use Eulerian methods? Do you want to get started on this, Stephen? You have some thoughts?
So in general, Eulerian methods would be better because you've got you're explicitly resolving diffusion, you're explicitly doing convection, and all of that's lost from a Lagrangian point of view. You've only got the effective signal for Lagrangian. The advantage of Lagrangian is that it's a lot more computationally efficient. So where there are 1,000,001 experiments that if I could run them from an Eulerian point of view, I would absolutely love to. But the simple fact is that I don't have the resources available to do that. It would require a lot of computational time to rerun these experiments, rerun the model online, and especially in the case of what I was doing, releasing things monthly for, 3-4 decades, that would require lots of discrete experiments to be started, which the resource simply isn't there. So the advantage of Lagrangian is that you can do a lot of different stuff, whereas with Eulerian, there's physics that you've got in there, which I'm having to completely skim over and can justify why it's acceptable and why advection is the main thing we care about. But if you could include convection, if you could include diffusion as well, that would certainly improve it. So the only real reason that you would use Lagrangian is because it's not physically possible to do the same thing with, or at least it's not practically possible to use online Eulerian runs for that many experiments.
So just now, Stephen compared in his talk. So he compared the online Eulerian method and the offline Lagrangian method. So actually, if my understanding is correct, you can do online Eulerian and offline Eulerian, online Lagrangian and offline Lagrangian. So there are 4 different methods actually. So I would say it will be really interesting to have a systematic comparison of the 4 different methods and see how they behave from, how different they are from each other and what's the impact on their individual implications. So so currently, Wilbert and I are working on a offline Eulerian method. So we're doing a offline model development, which we call it FIOPS. And we're still testing all the code, and hopefully it can work in the next few months. But it's all on the Eulerian side. So it will be interesting to have a systematic comparison of all 4 different methods.
Oh, great.
You read my mind, and so
not just into, oh, sorry, I'll let you go.
Sorry, Steve. You read my mind, and we're all Arctic or polar people here, and so so we're talking about these 2 studies you guys did, but other people. So no one's done this in other parts of the world ocean.
No, I haven't seen this. I have seen many people are doing the online Lagrangian method. So there have been quite a few, like there are a few recent ones. They are trying to understand how much the Labrador Sea water can be transported into the tropical Atlantic. So they're releasing all the tracers, all the particles over the section at the Labrador Sea and see where it goes, what's its final location. So I think there are quite a few studies out there. Stephen's study is the first one that I've seen for the offline trajectories, particles. But I haven't seen anyone doing like a very systematic comparison before.
Well, I'm gonna add a little something here to the 2 approaches. I think it's a false idea that the Lagrangian is cheaper computation-wise. If you want to do it right and have the same resolution as and not interpolation in time, if time scale is very important. Like if we are talking about the daily versus the monthly versus the yearly variability, then it will be very, very expensive to save all the output of the model to be able to drive your particles. And if 100, 1,000 might not be enough, you might have to go to 10,000. So the Lagrangian is that has the advantage that is you don't need to have as many particles to really look at the transport. is more natural coming from the Iranian. The other thing is that if you have behavior to your particles, now the salinity doesn't have any behavior necessarily, but if you have behavior, you are stuck with the particles to look at the transport. So it depends upon the scale you want to look at, the domain you want to look at, and the question you have. So I don't think it's one versus the other is better. It's exactly what you want to assess. And even for what you have done for the freshwater, I believe that if diffusion is important, then you cannot do a Lagrangian. You're going to have some results, yes, but what they mean, I'm not sure.
So in principle, you can, where diffusion is important and keeping computational costs down is important as well, it is in principle possible to add at least some element of diffusion into Lagrangian techniques by basically adding a random walk to the particles, and then the length scale of random walk being based on the turbulence in the model at whichever given point you're at. So that there is kind of a compromise if you want to try and go down that route as well. So it's, again, even further, not being just the binary, you can do one or you can do the other. You can start to try and play around more with...
I do agree with you that you can do a random walk, but the random walk is not exactly what you have. And it has been shown that depending upon how you do your random walk, you will have two different answers.
Oh yeah, of course.
And also, it's, as I say, it depends upon the time scale, because then you're going to have to save also your flow field and the time scale and resolution that is needed to address the problem.
Oh, definitely. The part of the one of the niceties of what we're doing with this is we have from somewhere in the 1950s up to, I think 2015 is the most recent that's been added, 5-day means at 12th degree resolution, which was calculated and saved for some other project, and in a kind of nice value for money for whoever's funding the research point of view, using pre-existing output to do new experiments is, well, you're getting twice as much science for the same funding, basically, because you're reusing something that already exists and getting extra value from it.
I was going to add on to what Stephen's saying there. One of our use cases has been that we have this big 40-member large ensemble that has 150 years of daily data for each of these runs. And of course, we didn't have these sort of tracers implemented at the time. And so it's something to do after the fact, that you can go back and reanalyze these older experiments, which is a really nice value, as Stephen's saying. So it's just, I think it is really just sort of a, if you've already put the cart in front of the horse by forgetting to put the tracers in or whatever, or not turning them on, then at least you can still get value out of it afterwards, you know. So.
Just to make sure, in case it wasn't already clear, that's exactly what I did in the paper that I was discussing. It's using pre-saved output that wasn't calculated specifically for my experiments at all. It was just using the Lagrangian analysis to extract extra value from that research.
And I want to add that I didn't say that the added value is that you might have different results and you have to be careful in your interpretation. That's it. But the adds for sure have value to do the Lagrangian.
I'm afraid we have to cut this discussion short. Some people have to go to other meetings. But I guess we have to, we don't have any time for community updates anymore, I'm afraid either. But thank you very much for the very useful discussion, and thanks to Stephen and Yashu for their very, very insightful presentations. Shall we still hand it over to Anne-Christine?
Yeah, the only thing that I wanted to mention to the modeling group is that Arctic Observing Systems Group has raised an interest in having a joint meeting in May. And they want to talk about using modeling to understand observing system and parameters. And I just wanted to see what your guys' interest is in having a joint meeting that month.
It sounds interesting. We'll have to discuss that with, I don't know what else we have on the schedule for May already, so, but it would be definitely be of interest to us.
Okay, I'll just reach out to you then.
And Wilbert, you
Okay.
can, Anne's got to go. I can stay on for another couple minutes if anyone has community updates that they need to share.
And they can also post them on the website, right? On the IOPIC collaborations.
Yeah.
Put them in a comment box.
Yep, I will get a link to that, where it'd be best to do that right now.
Well, I'll just say thanks. That was very interesting.
Speakers.
Thanks, it was.
Yeah.
Oh, thank you very much for inviting me.
All right. Thanks, Stephen. Appreciate your being on here. It's great.
Oh, thank you very much.
All right. I guess this will end the meeting for today. Thanks very much, guys. Thanks, Ben.
Thank you. Goodbye for now.
Okay, bye.
Bye, guys.
Bye-bye.